This is the 2006 higher level question on particle physics. So it's a good while ago, back in 2006, but there hasn't been a similar one since. So whether they've been saving it or they felt it was a bit tricky, I'm not sure which. So they start off by saying, during a nuclear interaction, an antiproton collides with a proton. Pair annihilation takes place and two gamma rays, which are photons of the same frequency, are produced. So that's setting our scene. So first off, they ask what is a photon, and a photon is a bundle, packet, or quantum, any of those three words, of energy. Then we have to calculate the frequency of the photon produced during the interaction. So we start off with the equation. It's the proton and the antiproton in the pair annihilation. So that's a symbol for the antiproton, P with the bar on top. And that gives us two photons of light, so two gamma rays, two flashes of light, scintillations. We have to calculate the frequency. So we start off, as always, we get the mass which has been annihilated. So the mass of a proton from page 47 in my tables, that's the same as the mass of the antiproton, so they're both this thing here. So they're annihilated, this mass is converted to energy, so E is equal to mc squared. But the mass here is two particles, so we have to double the mass of the proton and multiply it by the speed of light squared. Now, I didn't spot this until I finished the question, but they do give us these figures at the bottom of the page. I took them from the table, so that's why I got a few extra decimal places in there than what you probably use given the numbers at the bottom. So the energy that is produced in this pair annihilation is 3.006554848 by 10 to the minus 10 joules. And then I round that off to 3.0066 by 10 to the minus 10 joules. Again, I kind of forgot, but keep track of your scientific notation in your places. So this is the energy that's produced, but that's not what I was asked. I was asked for the frequency of the photon produced. So what I do then is I use my formula E is equal to HF. So E equals HF, I can rearrange that because I'm looking for the frequency, so I divide it across by H. I do the algebra before the substitution to save myself writing out these big long numbers over and over. Again, on page 47 of the tables, I find what Planck's constant is, which is 6.6260693 by 10 to the minus 4 joules per second. And again, that's given at the bottom of the page with a few less decimals. So I take my overall energy produced and I divide it by Planck's constant, and that gives me a combined energy of light of frequency this. So I didn't split the two up, but I am told in the question that two rays of the same frequency are produced. So I could take this frequency here and then split that in two. So that's the combined frequency. So I split it in two and I get the frequency for one. I would have divided the energy by two. That's probably a bit of a better way to go about it, because that energy is split between the two of them. Then you would have half of that value on top of Planck's constant to get the frequency of 1, but it's the same thing mathematically. So your answer, whichever way, is 2.2688 Hertz, and again, remember to include your units. The question moves on then to ask some of the background theory questions that will go along with this, such as, why are two photons produced? And two photons are produced so that momentum is conserved. Then we have to describe the motion of the protons after the interaction. So the photons travel in opposite directions. They would have the same speed and frequency. So we were told that previously, but that's how it will go. So they have to go in opposite directions again to conserve momentum. How is charge conserved in these reactions? Well, before we have a proton, which is a charge of +1, and we have an antiproton, which is a charge of -1. So before, the charge is 0. Afterwards, as photons are uncharged, the charge afterwards is 0, so the charge before equals the charge after, so charge is conserved. Then we have, after the annihilation, pairs of negative and positive pions are produced. Explain why. So I just underline these things because we have to explain both parts. So we have to explain why pairs and negative and positive are produced. So pions are produced as energy is converted into matter. So that's where the pions come from, energy being converted into matter. So mass energy is conserved and mass energy has to be conserved. So that's why they're produced. So after the annihilation, that's why pairs are produced. And then they must be positive and negative. The pairs must be produced in order to conserve momentum, and they must be of opposite sign to conserve charge. So there are three conservations: mass energy, momentum, and charge. Next bit then is, it tells us that pions and mesons consist of up and down quarks and their anti-quarks. So that would be the anti-up and the anti-down. Give the quark composition of 1 a positive pion and 2 a negative pion. So mesons are the smaller of the particles, and they just consist of a quark and an anti-quark. So we can pair those off down here. We have the up with the anti-down, or the down and the anti-up. This would give a positive pion because the up is 2/3 positive and the down is negative 1/3, so that giving us a positive. And this here with the down and the anti-up, that gives us the negative. So there are 6 types of quarks, which are also known as flavors. So the flavors of quarks are up, down, strange charged, top and bottom. So in this last part of the question, they bring in some half-life. So it tells us a neutral pion is unstable with the decay constant of 2.5 by 10 to the 12 per second. What is the half-life of a neutral pion? So we have to go to page 63 of our tables, radioactivity, and we find that T1/2 is equal to ln2 over lambda. So ln2 is a constant at 0.693. You can get that on your calculator. On my Casio, the ln button is above the 10. T1/2, that's the half-life. So again, some computer game players out there, this is the symbol using the game half-life, but T1/2 is actually the half-life. This is the decay constant. So we have all the figures we need. The decay constant is 2.5 by 10 to the 12 per second. That's our formula for half-life. That's 0.693. So we take 0.693 over this, and that gives us our half-life. So that's the half-life in these calculations of the neutral pion. Now I've got a couple of notes to finish. So the half-life for leptons, mesons, and baryons is given on page 48 of the tables. So it's going to say you could use that page to check your answer, but the listed figure is 5.82 by 10 to the minus 17 per second. So that's very different, mostly in that powers. So they're a difference of by 10 to the minus 4. So they're not actually that close, so it's not useful. Check the marking scheme, that is the correct answer. So it's unreliable in this case, but it could be useful in the right circumstances. So there are a lot of half-lives there. So some half-life calculations, that page 48 might kind of let you know if you're right or wrong. But as you can see here, it's not the be-all and end-all. The different figures will give you different answers. And then, like I said earlier in the video, the figures for the speed of light, the mass of the proton, and Planck's constant were given at the end of the question. I didn't spot them, so I should have used them here. It's kind of the typical thing. It's always a good idea, as your teacher probably tells you, to look through the full question before you start, and then to kind of read over as you're going as well, just so you don't miss information and make your life kind of a lot more tricky than it would be in some cases. So again, this part in particular here was a difference. We had some pair annihilation stuff as well, which might be a bit new. So you got your pair annihilation as well as your pair production, kind of reverse processes, and then this one then was kind of tagged in the 2006 question.